Log on, tune in, find out. Another good idea from Cambridge.
Please let me start. My talk will be devoted to Chebyshev polynomial approximations for some hypergeometric systems of differential equations, and my pleasure and honor to speak here on the discrete systems and special functions workshop in the Isaac Newton Institute for Mathematical Sciences in Cambridge University. Probably my talk will be more numerical than other talks in this session, and I'd like to emphasize some discrete values which are quite important for my talk. First of all, I published the tables of modified Bessel functions of complex order, and the idea of tables, of course, were discrete tables of special functions, and then it was necessary for us to interpolate the values of special functions. And the second, which I'd like to mention, that I use the polynomial power series and Chebyshev polynomials approximation for the computation of modified Bessel functions, and this idea is also discrete because when it's necessary for us to go to the other value of the independent value, it's not necessary for us to repeat whole process of the computation from the whole beginning, and it's sufficient for us only to do some additions and multiplications. So the hypergeometric type differential equations of the second order with polynomial coefficients and their systems are considered. The realization of the Lanczos tau method with minimal residue is proposed for the approximate solution of the second order differential equations with polynomial coefficients. The tau method was extended for the systems of the scheme of tau method was extended for the systems of hypergeometric type differential equations, and its scheme was applied to the approximate solutions of the systems of differential equations related to the differential equation of hypergeometric type. Various vector perturbations were discussed, and our choice of the perturbation term was a shifted Chebyshev polynomial with a special form of selected transition and normalization. The minimality conditions for the perturbation term were found for one equation. They are sufficiently simple for the verification in a number of important cases. The case of modified Bessel function of pure imaginary and half plus I beta order was quite important in the connection with Kontorovich-Lebedev ordinary and modified integral transforms, which were introduced by Professor Lebedev from St. Petersburg Physics Technical Yofe Institute. The codes of evaluation were constructed, and tables of the modified Bessel functions were published. The effective applications for the solution of some mixed boundary value problems in which domains and some theoretical physics problem were given. So we consider the following for the following differential equation of hypergeometric type of the following with polynomial coefficients and the following initial value problem for it. By its using nth approximation of the solution is sought in the form of the nth degree polynomial, which is the exact solution of the following Volterra integral equation with the addition in the right side on the following shifted and normalized Chebyshev polynomial n plus 2 degree. The coefficient of this Volterra integral equation we can easily obtain from the coefficients of the first differential equations. And here alpha is the most left root of the shifted Chebyshev polynomial of the n plus 2's degree in the interval 0, 1, and tau undefined coefficient. We can consider the problem of determination of the polynomial, which is the last deviated from 0 on the interval 0, 1 among all degree polynomials satisfying of the pair of linear correlations on the following coefficients. And for example, as a consequence of a number of considerations, the following theorem was proven that if the sequences of the numbers ci is alternating, then the polynomial is of the following form, Chebyshev polynomial of the following form with undefined coefficient is the polynomial least deviating from 0 in the uniform metric on 0, 1 among all polynomials of degree n satisfying the indicated pair of linear relation. On the basis of this theorem, it was shown that suggested by us in the tau method residual is the minimal in the uniform metric on 0, 1 among all possible polynomial residues permitting the Volterra integral equation solution in the kind of polynomial. It gives us possibility for the hypergeometric function and for the modified Bessel function Ki beta to find this residue in this form. It was compared with other tau method residue additions, and it was shown that this choice of the residue is the best as a theoretical and the concrete numerical computation cases. For the approximation of the modified second kind modified Bessel functions Chi beta at x, we have the following differential equations with polynomial coefficient of the following form and the Volterra integral equations of the following form. We can obtain the following recurrence formulas for the coefficients of the canonical polynomials, Lanzas canonical polynomials, which is sufficient easy to perform on the computer. The minimality of residues suggested by us follows from the theorem 1 in the connection with this equation, with this equality. The advantage of this modification is shown. The case of the system of the differential equations, equations of hypergeometric type with arbitrarily polynomial coefficients was considered. The following system of differential equations with the following initial values on 0, 1 with unknown vector function can consist from k coordinates. It's assumed to have only one solution. Integrating twice and carrying an addition in the right part in the kind of the vector polynomial, we derive for the determination of the nth approximation of the solution the system of Volterra integral equations with polynomial kernels in the form of the arbitrary addition of the polynomial n plus 2 degree on the interval 0, 1. The coefficients b we can connect it with the coefficient of the initial differential equations and p n plus 2 polynomials n plus 2's degree. The different variables of the vector residual choice and its minimization were analyzed. It was attempted just to use the simplex method for the obtaining solution of the minimization problem. But in analytical form, in this case, was impossible for us to obtain the form of the best polynomial in the right-hand side. And different just different cases were considered in the numerical case, and it was also used the Chebyshev polynomials with additions and shifted Chebyshev polynomials with additions and normalizations. And the recurrent formulas for the canonical vector polynomial coefficients convenient for the calculations were given, and the idea of the canonical polynomials it was possible to find in the book of Lanzas on the numerical analysis, but the case of the canonical vector polynomials, it was impossible to find in his book, and the idea of the canonical vector polynomials was introduced for the vector case was introduced by me. We can consider the system of two second-order differential equations in more detail. This case is of particular interest for differential equations with complex coefficients. It's convenient also for deriving polynomial approximation for hypergeometric and confluent hypergeometric functions of the first kind with complex parameter. We can consider the case of the modified Kantorovich-Lebedev integral transforms with kernels of the following form: a real and imaginary part of k half plus I beta at x function, where k is a modified Bessel function or second kind or McDonald function, which has a great importance in solving of some problems of mathematical physics, in particular mixed boundary value problems for the Helmholtz equation in wage and coin domains. These functions also occur in solution of some classes of dual integral equations with kernels which contain Macdonald function of pure imaginary order. In this case, we have the following system of two differential equations with the following initial values, or the system of corresponding Volterra integral equations. And by means of computation, it was shown that the choice of the residua in the following form is optimal as compared with other known variants, in this case too. But the complete analytical proof that this choice is the best, it was not possible to perform. So this is the formula of modified Kantorovich-Lebedev integral transforms with this function as a kernel. The first pair and the second pair of this transform, which were introduced by Lebedev, and the verification of the solution of singular integral equations of the following form was performed, and the proof of the Parseval equality for these transforms was conducted, and the problem of the evaluation of the modified Kantorovich-Lebedev transforms is simplified by means of their decomposition in the form of compositions of more simple integral transforms, in particular Fourier and Laplace transform. And it's possible to consider these transforms also as a case of the general Mayer integral transforms of special index and argument. The following dual integral equations with Macdonald function of the imaginary order in the kernel of the following form were introduced by Lebedev and Skalskaya, where G and F are given functions. They showed the solutions of these equations may be determined in the form of single quadratures from solutions of second kind Fredholm integral equations with symmetric kernel containing Macdonald function of the complex order in the following form. I'd like to change here the sheet. Sorry. This is the case of the equation, Helmholtz equation in the wedge domain with the following boundary value conditions, and this is the form in this domain. The function and normal derivative are given on the path on the boundary. And this is the form of the solution, the form of the solution, the form of the solution, the form of the solution. And we have the following formulas for the solution, where from some integrals of modified Bessel functions, and the numerical solution was conducted, and the economical methods of the evaluation of kernels of the integral equation based on Gauss quadrature formulas on Laguerre polynomial knuths were proposed, and the procedures of the preliminary transformation of integrals and extraction of the singularity in the integrand were used for the increase of accuracy and speed of algorithms. The case of dual integral equations admitting complete analytical solutions were considered, and examples given by us demonstrate the efficiency of this approach in the numerical solutions of the mixed boundary value problems of elasticity and combustion in the wedge domains. So the following problem was considered, and it was shown that it was possible to find the solution of the following Helmholtz equation in the form of single quadratures from the Fredholm integral equations type. What's important, the dimension of the problem is lowered on unit by this. What is the essential advantage of this method? And again, the examples permitting the complete analytical solutions of the problem were given. The numerical solution of the mixed boundary value problems and received dual integral equations were carried out. It consisted from numerical solution of the second kind, Fredholm integral equation with symmetric kernels, and the following taking of the quadratures from their solutions. The considered examples demonstrate the efficiency of the dual integral method in the solution of the mixed boundary value problem for the Helmholtz equation in the wedge domains. This work has been partially supported by the Civilian Research and Development Foundation grant, which is finished already, and it was together with Dan Lozier and Bruce Fabionis from National Institute of Standards and Technology in US, and the joint paper was prepared, and the powerful benchmark algorithm was used by Fabionis and Lozier for the McDonald function in the general complex domain, and it was shown together just that this tau method approach may be extended from the domain in which it was used from 0 to 10 for more biggest domain of variables, and when it is possible to use this approach is not everywhere, of course, but this approach is one of the most economical in this case. And I'd like to show some pictures about some applications, if I have some few minutes. This is about boundary value problems. This is the picture about some theoretical physical equations and some applications of modified Bessel functions in the case of dipole and quadruple radiation. And this is one of the hypotheses which was done by me about monotonicity of these functions and these multiplications. It has a physical explanation, but it's I work on the proof of the monotonicity of this multiplication till this time. And here are some inequalities which were used for the modified Bessel function of half plus I beta order and pure and complex order, which were used for some theoretical statements. And what I'd like to show you also some. This is the formula for hypergeometric function. The formula for the hypergeometric function was the formula for the coefficients of the canonical polynomials for them. You can see that the formulas are not so complicated in this case, for the case of hypergeometric function. And this is some more quadrature formulas for this function, some integral representations for this function, and some quadrature, Gauss-Legendre quadrature formulas for this function. And this is the picture. This is also quadrature. This is the picture of the computation of tables of these functions. This is the table for the real part of this function, and this is the figure for the imaginary part of this function. The tables of this function were computed in this field, x from 0 to 10 and beta from 0 to 10 also. And in this and the pictures are approximately the same for the real and imaginary parts. In domain 1, the power series approach was used. In domain here, domain first, and domain 2, the tau method approach was used. And in domains 3, the quadrature formulas were used for the computation, and a joint code based on all of these three approaches was constructed. Thank you very much for your attention.
So is the code of your computation of these McDonald's functions available in some numerical library?
It's the parts of it are available. It was available a time ago, but in the connection with the first version of the codes available, but now it's not available, unfortunately. But I can.
But since you've collaborated with Dan Loescher, he has working with many of those libraries, so I would imagine that he would put it in such a library.
He has my code, but they use more general codes now. More general codes now.
Well, let's thank Juri. Thank you very much.